Let us start with the definition of physical quantity. The quantities that can be measured are called physical quantities. Physical quantities are of two types. The first being fundamental quantity. The physical quantities which are independent of other quantities are called fundamental quantities. They are 7 in number, which are depicted in the following tabular column. The quantities are mass, denoted by the symbol m, measured in kg; length, denoted by L, measured in meter; time, denoted by T, measured in seconds; temperature, denoted by theta, measured in Kelvin; intensity of light, denoted by CD, measured in candela; current, denoted by I, measured in ampere; amount of matter, denoted by N, measured in mole. Supplementary fundamental quantities. Apart from the 7 fundamental quantities, there are 2 supplementary fundamental quantities, which are plane angle measured in radian and solid angle measured in steradian. Now moving on to derived quantities. The physical quantities which are derived from fundamental quantities are called derived quantities, except the above 7 fundamental quantities and of course 2 supplementary fundamental quantities, that is 7 plus 2 quantities. All other remaining physical quantities that we come across in physics are all derived quantities. Let us learn the definition of unit. The device or the system used to measure a physical quantity is called a unit. Moving on to the definition of dimensional formula. The powers to which fundamental quantities are raised to obtain the unit of a physical quantity is called dimensional formula. Dimensional formula can be derived in two forms. The first one from the formula of the physical quantity. Example for this is velocity. Velocity is obtained from the formula displacement by time and is represented as v is equal to s by t. Here displacement is represented by L1 and time is represented by T1. Thus, V is equal to S by T has a dimensional formula L1 by T1, which can also be written as L1 T power minus 1, which can also be written as L1 T minus 1. Thus, the dimensional formula of velocity becomes M1 L1 T minus 1. Thus the dimensional formula of velocity becomes m0, since we don't have a quantity called mass in the above formula, L1 T minus 1. Dimensional formula can also be obtained from the unit of a physical quantity. We'll take an example here and check it out. Acceleration. The actual unit for acceleration is meter per second square. Meter has a dimensional formula L1 and second square has a dimensional formula T2. Thus the dimensional formula of acceleration can be written as L1 T minus 2. Therefore, the dimensional formula of acceleration becomes m0, as we don't have a quantity representing mass in the above equation, L1 T minus 2. So, this is how to derive dimensional formula of different physical quantities. Let me give you a small hint. Once you learn the dimensional formulae of 5 different physical quantities, you can easily derive the dimensional formula of most of the physical quantities in physics. The 5 basic dimensional formulae are mass m1, length L1, time t1, velocity L1 t minus 1, acceleration L1 t minus 2. Knowing the dimensional formulae of these quantities called mass, length, time, velocity and acceleration, the dimensional formulae of most of the physical quantities that we come across in physics can be derived. Knowing these, now let us complete the task of learning dimensional formulae of different physical quantities. We start with displacement, the easiest one among all. Displacement is nothing but length, hence it can be written as L1. Next, area. The formula for area is length into breadth. Length is represented in dimensional formula as L1 and breadth is also represented as L1. Thus L1 into L1 become L2. So the dimensional formula of area is M0 L2 T0. As we don't have representation for mass and time here, we had taken them as 0. The next one, volume. The formula of volume is length into breadth into height. Length is L1, breadth is L1 and height is L1 again. So volume is L3. Since we don't have any representation for mass and the time, the final dimensional formula of volume can be written as M0 L3 T0. Next, density. Density is the ratio of mass to volume by the formula. Mass is M1 and volume, as we had just found to be L3. Substituting both mass and volume in this formula, we get M1 by L3, which becomes M1 L minus 3 T0, as time does not have any representation here. The next one, specific gravity. Specific gravity is the ratio of density of body to the density of water. If we just observe, it is the ratio of two similar physical quantities which are density in the numerator and density in the denominator. Thus both of them get cancelled. Thus this does not have any dimensional formula. So we understand that the ratio of similar physical quantities does not have dimensional formulae. The next is linear density. Formula for linear density is mass by length. Mass has a dimensional formula M1, length has a dimensional formula L1. Thus linear density has a dimensional formula M1 L minus 1 and T0. Speed. Speed is given by the formula distance by time. Distance is nothing but length represented by L1 dimensionally and time is represented by T1. Thus it becomes L1 T minus 1. As we don't have a representation for mass here, we take it as M0 L1 T minus 1. Velocity. The dimensional formula for velocity is explained while I was explaining you the method of calculating dimensional formula of a physical quantity. Here velocity is displacement by time. Displacement is L1, time is T1, so it becomes L1 T minus 1. As we don't have any representation for mass, let us take it as 0. Thus the final dimensional formula of velocity is M0 L1 T minus 1. Next is acceleration. By formula, acceleration is change in velocity by time. Change in velocity is nothing but velocity. As we have the dimensional formula of velocity as L1 T minus 1 here, let us represent it, and in the denominator it is time given by T1. Thus the final dimensional formula of acceleration becomes L1 T minus 2. Of course we don't have representation for mass, let us take it as M0. The next is momentum. Momentum is the product of mass and velocity. Mass is given by M1, velocity is given by L1 T minus 1. Thus for acceleration it becomes M1 L1 T minus 1. Next is force or weight. The formula for force F is equal to ma. The formula for weight W is equal to mg. Acceleration A can be taken as acceleration due to gravity g. Thus this force and weight have the same dimensional formula, mass into acceleration. Mass is m1, acceleration is L1 T minus 2. Thus the dimensional formula for force or weight is m1 L1 T minus 2. Next, impulse. Impulse is given by the product of force and time. Force, as we had just found, it is m1 L1 T minus 2 into time is T1. So the final dimensional formula of impulse is m1 L1 T minus 1. Now let us calculate the dimensional formula for the physical quantity work. From the formula of work, we have work as the product of force and distance. Force is m1 L1 T minus 2 and distance is L1. Now this becomes m1 L2 T minus 2. So this is the dimensional formula for work. The dimensional formula for kinetic energy. Kinetic energy is expressed by the formula half mv square. The numbers like 1, 2, 3, 4, 1 by 2, 1 by 4, etc. These does not have dimensional formula. Hence we can ignore 1 by 2 here. Going with the remaining terms, mass has the dimensional formula m1 and velocity has the dimensional formula L1 t minus 1. Since we have square here, let us take it 2 times. Now the entire formula becomes m1 L2 t minus 2. The next one, potential energy. Potential energy has a formula PE is equal to mgh. Here m has the dimensional formula m1. G, acceleration due to gravity, has the dimensional formula L1 t minus 2 and height has the dimensional formula L1. So the entire thing becomes m1 L2 t minus 2. The next one, power. Power is the ratio of work to time. So work with the dimensional formula m1 L2 t minus 2 is taken in numerator and t1 in the denominator. Now this becomes m1 L2 t minus 3. The next one, coefficient of restitution. From its formula we have coefficient of restitution as the ratio of relative velocity of separation to the relative velocity of approach. This is the ratio of two similar physical quantities. This does not have units at all. Thus we can represent the dimensional formula of coefficient of restitution as m0 L0 T0. The next one, pressure. Pressure is the ratio of force to area. We have the dimensional formula of force as m1 L1 T minus 2 by area is L2. So this becomes m1 L minus 1 T minus 2. The next one, stress. Stress has the formula force by area. So its dimensions will be almost similar to pressure. The next one, thrust. Thrust has the formula pressure into area. We have the dimensional formula of pressure as m1 L minus 1 T minus 2 and area as L2. So the dimensional formula for thrust becomes m1 L1 T2. The next one is the strain. Strain has a formula change in dimension by original dimension. As this is the ratio of two similar physical quantities, this does not have any dimensional formula. Thus it can be taken as m0, L0 and T0. The next physical quantity is modulus of elasticity. The formula of modulus of elasticity is stress by strain. We know strain does not have any dimensional formula. So modulus of elasticity will have the same dimensional formula as stress. So it will be m1 L minus 1 T minus 2. Young's modulus will be the ratio of linear stress by linear strain. Rigidity modulus will have the formula shearing stress by shearing strain, and bulk modulus has the formula volume stress by volume strain. Whatever the type of strain it may be, strain does not have any dimensional formula. So Young's modulus, rigidity modulus and bulk modulus will have a similar dimensional formula to that of stress, which is m1 L minus 1 T minus 2. So Young's modulus, rigidity modulus and bulk modulus will have the same dimensional formulae, which is m1 L minus 1 T minus 2. Poisson's ratio. Poisson's ratio is the ratio of lateral strain to linear strain. Since it is the ratio of two similar physical quantities, it does not have any dimensional formula. So it will be m0, L0, T0. The next one, couple or moment of force. The formula for couple or moment of force is force into distance. Force has a dimensional formula m1 l1 t minus 2 and distance l1. So this becomes m1 l2 t minus 2. The next physical quantity is torque. Torque is given by the product of force and distance. So for force, the dimensional formula is m1 l1 t minus 2 and for distance it is l1. So for the torque it becomes m1 l2 t minus 2. The next physical quantity is surface tension. Surface tension has a formula force by length. Force has a dimensional formula m1 l1 t minus 2 by length l1. So it becomes L1 and L1 get cancelled. So the dimensional formula of surface tension becomes M1 L0 T minus 2. The next one, spring constant. Spring constant also has the formula force by length. So its dimensional formula will resemble the dimensional formula of surface tension, which is M1 L0 T minus 2. The next one, surface energy. It has a formula work by area. Work has a dimensional formula m1 l2 t minus 2 by area is l2. L2 and L2 get cancelled. So surface energy has a dimensional formula m1 l0 t minus 2. The next one, force constant. Force constant has a dimensional formula force by length. If we just observe, this formula is similar to the formula of surface tension and spring constant. So force constant also has similar dimensional formula to surface tension, which is m1 l0 t minus 2. The next one, coefficient of viscosity. This has a formula force by area by velocity by distance. Force has a dimensional formula m1 l1 t minus 2 by area L2 by velocity L1 t minus 1 by distance L1. On simplification, we get m1 l minus 1 t minus 1. The next one, rate of flow. Rate of flow is given by volume by time. Volume has a dimensional formula L3, time has a dimensional formula T1. So rate of flow has a dimensional formula m0 l3 t minus 1. Radius of gyration. Radius of gyration has a formula equal to distance. So its dimensional formula will be m0 l1 t0. The next one, inertia. Inertia is measured by mass. Hence inertia will have a dimensional formula equal to mass, which is m1 l0 t0. The next one, moment of inertia. It has a formula mass into distance square. Mass is m1, distance is l1 whole square. So it becomes m1 l2. Intensity. Intensity has a formula force by mass. Force is m1 l1 t minus 2 by mass is m1. m1 and m1 get cancelled. So the dimensional formula for intensity is m0 l1 t minus 2. Gravitational potential. Gravitational potential has a formula work by mass. Work is m1 l2 t minus 2 by mass is m1. m1 and m1 get cancelled. Gravitational potential has a dimensional formula m0 l2 t minus 2.
The next one, gravitational constant. The formula for gravitational constant comes from Newton's universal gravitational law, which is F is equal to G capital M small m by R square. From this, capital G is equal to F R square by capital M small m. Simply it can be written as force into distance square by mass square. Force is m1 L1 t minus 2, distance square is L2 by mass square is m2. On cancelling masses in the numerator and denominator, we get the gravitational constant's dimensional formula as m minus 1 L3 t minus 2. The next one, orbital velocity. Orbital velocity V0 is given by square root of gr. Otherwise, simply it can be considered as velocity, and we know velocity has a dimensional formula L1t minus 1. So, orbital velocity will be having a dimensional formula m0 L1 t minus 1. The next one, escape velocity, generally given by the formula square root of 2gr, but even this escape velocity can be considered to be velocity, thus its dimensional formula also becomes L1t minus 1, otherwise m0 L1t minus 1. The next one, angle or angular displacement. The formula for angle or angular displacement is arc by radius. Arc in the sense length of the arc by radius. The length and radius both are equal terms, hence they nullify each other. Thus angle becomes a dimensionless quantity. So the dimensional formula of angle is also m0 L0 T0. The next one, angular acceleration. Angular acceleration is angular displacement by time. Angular displacement does not have any dimensions, and time square has a dimension t2. When this comes to the numerator, the overall dimensional formula for angular acceleration will be m0 L0 t minus 2. Next, angular velocity. Angular velocity is the ratio of angular displacement by time. Again, angular displacement does not have any dimensions. Time has a dimension t1. So, when this comes to numerator, it becomes t minus 1. Thus, angular velocity has a dimensional formula m0 L0 t minus 1. The next one, Planck's constant. From Planck's equation, energy E is equal to h nu. Otherwise, Planck's constant h is equal to E by nu. Energy has dimensions m1 L2 t minus 2. By frequency is t minus 1. On simplification, we get m1 L2 t minus 1. Next, time period. Time period is nothing but time. So, given by m0 L0 t1. Next, frequency. Frequency is number of vibrations by time. Otherwise, frequency is the reciprocal of time. So, it is t minus 1. Otherwise, m0 L0 t minus 1. Next, aerial velocity or diffusion constant given by the formula half r square omega. So, its dimensional formula becomes L2 t minus 1. Then the pressure gradient. Pressure gradient is change in pressure by distance. Change in pressure is also termed as pressure, and pressure has a dimensional formula m1 L minus 1 t minus 2 by distance L1. So, the final dimensional formula for pressure gradient becomes m1 L minus 2 t minus 2. The next one, velocity gradient. Velocity gradient is given by the formula change in velocity by distance. Change in velocity is also termed as velocity given by the dimensional formula L1 t minus 1 by distance L1. L1 and L1 get cancelled. The remaining term is t minus 1. So, the final dimensional formula for velocity gradient becomes m0 L0 t minus 1. Now let us learn the dimensional formulae of some of the quantities in the chapter heat. The first physical quantity is heat. As it is a form of energy, it will have the dimensional formulae of energy, which is m1 L2 t minus 2. Next, temperature. Temperature is a fundamental quantity with a dimensional formula K1. It can also be written as m0 L0 T0 K1. The next quantity, specific heat, is obtained from the formula Q is equal to mst, from where we can write S is equal to Q by mt, S representing specific heat, Q representing heat energy, m representing mass, and T representing temperature. Substituting the dimensional formula of all these, we can write S is equal to m1 L2 T minus 2 by M1 into K1. On simplification, we get M0 L2 T minus 2 K minus 1. The next physical quantity, latent heat. Latent heat is obtained from the formula Q is equal to ml, from where we can write L is equal to Q by M, L being latent heat, Q being heat energy and M being the mass. Now heat energy's dimensional formula is M1 L2 T minus 2 by mass is M1. M1 and M1 get cancelled, so the dimensional formula of latent heat becomes M0 L2 T minus 2. Next, coefficient of linear expansion. Coefficient of linear expansion is the ratio of increase in length to the original length per 1 degree centigrade rise of temperature. So, alpha is equal to L2 minus L1 by L1 into T2 minus T1. Here, L2 minus L1 is change of length and L1 is original length. These two quantities get cancelled and the difference of temperature T2 minus T1 will also be temperature, which will have a dimensional formula K1. When it comes to numerator, it becomes K minus 1. Thus, coefficient of linear expansion has a dimensional formula M0, L0, T0, K minus 1. Repeating the same method, you can find out the dimensional formula of coefficient of areal expansion and coefficient of volume expansion also. In coefficient of areal expansion, the similar terms called area get cancelled and difference of temperature alone remains. Hence, its dimensional formula is also K minus 1. Same is the case with coefficient of volume expansion. Here the difference of volume and the original volume get cancelled, leaving the difference of temperature in the denominator. When it comes to numerator, it becomes K minus 1. Thus, the coefficient of linear expansion, coefficient of areal expansion and coefficient of volume expansion all have the same dimensional formula K minus 1. The next physical quantity is coefficient of apparent expansion. The coefficient of apparent expansion is given by the formula gamma is equal to V2 minus V1 by V1 into difference of temperature. In the numerator, we have the difference of volume. The difference of volume in the numerator and the volume in the denominator, they can be nullified because they are the similar physical quantities. So the remaining is only difference of temperature, whose dimensional formula is K minus 1. So the final dimensional formula of coefficient of apparent expansion becomes M0, L0, T0, K minus 1. Moving on to the next physical quantity, coefficient of real expansion. The coefficient of real expansion have a similar formula like coefficient of apparent expansion. So this physical quantity also has the dimensional formula M0, L0, T0, K minus 1. Now let us learn the dimensional formula of certain constant. The first one, universal gas constant. From the universal gas equation, we have PV is equal to NTR. Otherwise, we can write R is equal to PV by NT, where P is pressure, V is volume, N is number of moles and T is temperature. When you substitute the dimensional formula of pressure, volume, number of moles and temperature here, we get the dimensional formula of universal gas constant as M1 L2 T minus 1 K minus 1 mole power minus 1. Next, Boltzmann constant. Boltzmann constant K is equal to R by N and its dimensional formula is M L2 T minus 2 K minus 1. Next, the Stefan's constant. It has a formula sigma is equal to Q by A T into T power 4. Here the small t indicates time and capital T indicates temperature. The dimensional formula for this becomes M1 L0 T minus 3 K minus 4. The next one, solar constant. It has a formula energy by area into time. When you substitute the dimensional formula of these quantities and then simplify, we get M1 L0 T minus 3. Next, mechanical equivalent of heat. The formula for this comes from Joule's law. which is W is equal to JQ. From this we can write J is equal to W by Q, where W is work and Q is energy. We know work and energy have the same dimensions, hence they nullify each other. Thus mechanical equivalent of heat is a dimensionless quantity, hence can be written as M0 L0 T0. Then thermal capacity, it comes from the formula Ms, where M is mass and S is specific heat. Substituting the dimensional formula of mass and specific heat here, we get M1 L2 T minus 2 K minus 1. Next, entropy. Entropy is nothing but the ratio of heat and temperature. Heat has a dimensional formula M1 L2 T minus 2 by temperature is K1. So the final dimensional formula of entropy is M L2 T minus 2 K minus 1. The next physical quantity is enthalpy coefficient. It is equal to heat, hence its dimensional formula is M1 L2 T minus 2. Next, conductivity, given by K is equal to QD by A into difference of temperature into time, where Q is heat energy, D is the distance, A is area, T is time, and of course this is the difference of temperature. Substituting the dimensional formula of all these and solving, we get M1 L1 T minus 3 K minus 1. Next, the thermal resistance. Thermal resistance is difference of temperature into time by time. The next physical quantity is thermal gradient. Thermal gradient is difference of temperature by length. Difference of temperature is also temperature, which is given by K1, and length is L1. L1 comes to numerator and the final dimension formula of this becomes K1 L minus 1. Following the same method as we had followed in deriving a number of dimensional formulae in different terms, we can arrive at the dimensional formula of some of the magnetic quantities and electrical quantities, which are explained here under. Let us move on to the very short answers in units and measurement. The first question is, distinguish between accuracy and precision. The accuracy of a measurement of any physical quantity made by any measuring instruments is a measure of how close the measured value is to the true value of the quantity. The accuracy depends on errors. Coming to the precision of the measuring instrument denotes up to what limit or resolution the quantity can be measured with the given instrument. The precision does not depend on errors. The next question in this series, what are the different types of errors that can occur in a measurement? The different types of errors that can occur in a measurement are systematic errors, random errors, and gross errors. The next question, how can systematic errors be minimized or eliminated? The answer, systematic errors can be minimized by improving experimental techniques, selecting better instruments, and removing personal bias as far as possible. For a given setup, these errors may be estimated to a certain extent and the necessary corrections may be applied to the readings. Next question. Illustrate how the result of a measurement is to be reported, indicating the error involved. To measure any physical quantity, we compare it with a standard unit of that quantity. No measurement is perfect as the errors involved in the process cannot be removed completely. Hence, in spite of our best efforts, the measured value is always somewhat different from its actual value or true value. The next question in this series, what are significant figures and what do they represent when reporting the result of a measurement? The answer, the digits of a number that are definitely known plus one more digit that is estimated are called significant digits or significant figures. The example, time period of a simple pendulum is 1.62. The digits 1 and 6 are reliable while the digit 2 is uncertain. The measured value has 3 significant figures. The next question, distinguish between fundamental units and derived units. The units of fundamental quantities are called fundamental units. Fundamental units can neither derive from one another nor can they be resolved into other units. Units of derived quantities are called derived units. The next question, why do we have different units for the same physical quantity? The answer is, we have different systems like CGS system, MKS system, FPS system and SI system. Hence, we have different physical units for the same physical quantity. The next question, what is dimensional analysis? The answer, dimensional analysis is the representation of derived physical quantities in terms of units of fundamental quantities. With the help of dimensional analysis, to check the correctness of the equation, convert one system of units into the other system and derive certain equations relating physical quantities. The next question in this series, how many orders of magnitude greater is the radius of the atom as compared to that of the nucleus? The answer for this, size of atomic nucleus is equal to 10 power minus 14 meter and size of atom is equal to 10 power minus 10 meter. Hence, the size of atom is 10 power minus 4 meter greater than the size of the nucleus. The last question in this series, express unified atomic mass unit in kg. The answer, 1 unified atomic mass unit is equal to 1 by 12 of the mass of carbon 12 atom. 1 AMU is equal to 1.66 into 10 power minus 27 kg.